So this question asks, upon forms as water collects in a conical depression of radius a and depth h, suppose water flows at a constant rate k and is lost through evaporation at a rate proportional to the surface area of the pond, which is the circle formed by the cone on top, with proportionality constant c. What is the ordinary differential equation for volume v of t of water in the pond at time t? Now, this one starts out fairly simple, but it gets pretty complicated pretty quickly. But the best thing you can do is remember that your total change in volume over time is going to be the in rate minus the out rate. So the change in the rate going in minus the change going out, and the rate going in is luckily very easy. It's just this constant k. For the for the evaporation of the water, we get this proportionality constant c times the surface area, and um, for the for the circular disc at the top of the cone of water, it's just c times pi r squared. Now the tricky part is that we don't have r or the height of the water, which I've labeled as y, given to us in our initial question. We just have the total radius of the whole depression A, and then the height h, and so we have to get everything in those terms. But luckily, because it's an inverted cone going downward here, the cone of water is proportional is a similar shape to the whole cone of the depression here. And so we can say that the radius of the whole cone divided by the height should be the same as the radius of the water cone divided by its height, y. And so I've written that here, a over h equals r over y. And so what you can do then is solve for r to plug into this equation. And so you get c times pi times the quantity of a over h times y squared, in which once you factor out the square through the product there, it looks like this. Now, we're still in a bit of a bind because we still have this y that we need to get rid of. Y was not one of our given variables or constants in the beginning of this equation. But we are finding an equation in terms of, we're finding the ordinary differential equation for the volume at time t. So we can actually use the volume of water at time t. So if we say at time t, the radius of the cone is r and the height of the cone of water is y, we can say that the volume at time t is just the volume of a cone, 1/3 pi times r squared times y, as our height and radius. Um, and now we can go back again and replace that r squared with a over h times y squared. And so once you work that out, this is the fraction that results times y cubed. I'm leaving the y cubed separate because we're going to solve for y. And so now if we divide by this constant out front on both sides, we get y cubed is equal to this constant in front times v of t. And then uh, take the cube root of both sides. So then y becomes this constant times v of t raised to the 1/3. And I left it 1/3 because when we're going to plug it back into our dv out dt, um, you're going to we're going to square it, so it's nice to have it be an exponential form. And also you've got this fraction of constants, this fraction of constants, and there will be some simplifying between the two, and it's best to get them both in terms of the same power. So I think I've given enough information that you can actually plug this into the dv out dt equation and then simplify it down. And then once you've done that, you can just plug it into this dv dt equals dv in minus dv out, um, and then get it into standard form if that's what your professor wants. If your professor doesn't want that, just leave it. You can leave it as is, but leave it as simplified as possible. Hope that helped, and best of luck.